see. HCl6. We'll take this. On the screen. As you can see. So here, if you can't let me know, I'm showing you the advertisements and sales example, which we took last time. The data here. Okay. So now we'll go with the scatter diagram quickly. Insert charge scatter diagram. Okay, so here we have the scatter diagram. So we have sales on the vertical axis and the advertisement expenditure is on the horizontal axis. Okay, that is how we had that. Okay, so now this relationship, we know it is positive. Okay, we know that the relationship is positive. So what is the best fit line is our question, right? So as I explained to you, we can imagine a certain line, but we don't know whether that line is the best line to represent. Okay, so I'll draw an imaginary line here. Okay, is that fit? Okay, I'll change the color to something else. Okay. Right. So this is the imaginary line I assume to fit this data with. Right. So as I explained, there will be still a question whether this is the best line. Okay, how to figure that out is our question, right? So the best fit line, as I mentioned, is the line that we can find, of course, using our equation. We can manually calculate that, okay? Or variance divided by variance of X. X here is the advertisement expenditure. Sales is the Y value. That is the option that we have. We can actually do it if we want. But of course, we have, with the computer, we have easier methods, right? The easiest is doing it on the graph itself, okay? So that is, you click on one of the dots here, okay? Then right click on that dot. Click on it, then right click. Click, left click first, then right click, okay? Then on the open menu, you can see an option called add trend line. Add trend line. So that option is there. Okay. So you click on that. So once you click, it will open with some options, right? So it says exponential, linear, logarithmic, polynomial, right? So various different options are given. Okay. So these things you still don't know, right? But linear, at least you know. Linear is the line that is, say, a straight line, right? That represents a straight line. Okay, so usually by default, it opens for linear. So this is the best fit line calculated by Excel using the least square method, right? Using the least squares method, this line is estimated by Excel. Okay. Right. So now we can see the line. Okay. So this my line is of course not the correct one, no? Even though I imagine like that. So I move it a bit of a side. Okay. I will use it later for a certain purpose. For the moment, I will move it. I can't move it. It has to be inside this. Okay. Anyway, so okay. Right. So now this line, what is the equation of this line? Right. So we don't know. So if you want to figure it out, of course, you can do it very easily. Like you can take 2 points on this line. Okay. By taking 2 points on this line, x value and y value, you can estimate the equation that is mathematics, right? You can do it. But of course, you don't even have to do that. Okay. Because if you click here again on this line, so you will see uh, the options for the line, right? Various option, formatting option, say color option. Then here again, if you go to uh, the line trend line option, that is the calculation of the line option. In the bottom area, right, you can see uh, this display the equation on the chart. Okay, so it will show you the equation. Okay, it will show you the equation on the chart based on the least square method. Okay, and there is another option to show R square value. So we have not discussed about that yet. Okay, then it also has the option to set the intercept to a certain value. If you click here, it will by default will set to 0. You can see the line is now going through 0. So if you know for sure when x is 0, y should be 0, you can set it like that. But for our data, we cannot say so, right? Even though we don't have any advertisement expenditure, we could still have sales. Okay, so therefore we can't say. So we can't put a tick there. Okay, so when you change it, you can see here also you don't see any C because beta not value, because for a line going through 0 point, we don't have a C value. Remember that? Okay. So, but we can't set it to 0, so we have to remove that tick. Or even if you know that when there is no advertisement expenditure, sales should be a certain value. Assume it is 10, it should be 10, right? So it is for sure. So we can set it like that also. Okay, now you can see the line stops there, but it goes through 10. That means when x is 0, that means when advertisement is 0, sales are 10. But actually, for this case, we cannot do that. Okay, hope you get that. Right, now, this line is the line that represents this data as the best fit, that is with the least squared errors sum, right? Sum of least squared errors. Or we cannot say sum, least sum of squared errors, right? Sum has to be the least, right? Least sum of squared errors are here. So that idea you need to understand because there are certain issues with this method. Okay. Now we are talking about the sum of squared errors. Now here, since the data are close by, it may be still reasonable. Okay. But if we have different data, right, this might cause a significant impact. Okay. Let's see. So for example, this value, right? Uh, that is at 1 it was 30. We'll change that value to 10. Okay, I'll draw a line here first to maintain the current line. Okay, this line represents the current line. Okay, so we'll change the value here. Okay, value there to 10. See what happens to the trend. Got it? It changed quite significantly from the original line because of change in one date. Okay, then let's change another value, uh, 50 here, right? Assume during that month the sales had been 20. See? While the general pattern is like this, you can see, right? General pattern is, if you look at it, it is like this. Okay. But because of this one data here, right? This line turns towards that. Why? That is because of the error. Now, this is quite far from the regular pattern. Okay. This is quite far from the regular pattern. And there is a large error. Okay. So this large error, when it is squared up, it becomes huge. Okay. It becomes huge. So to balance that, right, the calculation has to say turn the line towards that a lot to reduce that error, while of course increasing the error in the other areas. But still, the overall error, that is the sum of errors, will be at the minimum. Okay, so a thing to remember therefore is that this best fit line is significantly affected by a data, maybe a single data that is far away from the regular pattern. Okay. So this is a kind of risk. So that will, now you can clearly see, right? This line does not really represent the general pattern. Okay. It does not really represent the general pattern. Okay. We'll change that value to even lesser, be 10. Can you see? For some reason, just happened that month, the sales had to be 10. Okay. See the lines equation? Y equals minus some value. Even decimal, it is a minus value, a negative value. So negative slope, a small slope, but still a negative slope, which means when the advertisement expenditure is increasing, the sales are decreasing, isn't it? If you consider this line as the theoretical relationship. Get my point? Okay. So that is the risk relying on the data, right? So in that month, for some reason, it may have happened to be 10. But the general pattern is not like that. But if you consider that data, then you get a misleading interpretation. So you have to figure out whether this actually is a normal scenario or whether it is a special scenario. Okay. So maybe you find that it is a special scenario, right? So during that month, they have maybe say relocated the shop or something, right? So some special thing has happened during that month. Okay. And because of that, the sales were quite low. Or maybe some other thing, right? Maybe a natural scenario, right? Disaster, cyclones or something has been there. And as a result, say people were quite devastated, and these kind of products may not have had enough demand. So even though you advertise with a lot of effort, people don't buy because of the situation. Okay, so your sales are very low. So you have to figure that out. Okay, so if that is not a normal scenario, what is the situation? You have to first figure out. Right? Then you may figure that, okay, this is during this disaster context, which is not the regular scenario. This is a very special scenario, which does not happen often, right? So for that reason, you identify this to not to represent this theoretical relationship in the general scenario. Okay. After identifying that, what you have to do is, okay, what you have to do is remove this. Remove that data. Of course, you have to remove that by bringing this closer. And after that, you have to redraw this to do it properly. Anyway, you have to remove that data. Okay, understood. So once you remove, you cannot simply remove because it is just far away, right? We usually use the word outlier to identify that kind of a data. So you have to see why the outlier is. You cannot simply delete an outlier just because it is an outlier. Because if it is uh, not having any special reason to be there, then it is a normal scenario. So the normal scenario should represent uh, the theoretical relationship. Okay. So therefore you can't simply remove it. But if there is a special situation that you can identify, or special reason that you can identify why it is different from the general pattern, then you can remove it. So once you remove that, you can't stay silent about it. Okay. So you have to identify that this data was there and it had caused this to have this kind of a relationship, but it was then identified that that data is coming from this a special situation or special scenario. Okay, it is having this special background. Right? Because of that, it was removed, and then the data is reanalyzed to find this relationship. So that is how we have done it. Okay. So when you say that, it identifies that, okay, this relationship that you calculated without that data represents the situation without, or normal scenario without that special scenario. So you see, if you are representing this as, or presenting this as a model to say that this is the relationship between these two variables, then you have to say this is the relationship between these two variables except in that kind of scenario, which you have, you can't simply say that kind of, but you have to say what kind of scenario, right? Which you have removed from modeling this. Okay, is that clear? Right. Then I'll come to, or I'll use another method here. I'll use another method. That is finding of this equation using the statistical calculation. Now, of course, here also it does the calculation in the background to come up with the equation, right? But I will show you how to do that in the normal statistical analysis way using our analysis toolpack. So we go to data and to analysis toolpack, or data analysis actually, is the option, right? We open there and we select the regression analysis. So we just say regression, right? Regression. So regression analysis is the method that is used to find this equation. Okay. So I select regression analysis, or actually just say regression, select regression and go to OK. Then it will open this dialog box where I have the X range and the Y range here. So I will include the X range. X range is the independent variable data range. So I will include the advertisements expenditure as the X range because that is the independent variable. I included the label also there. Then for Y range, I include sales. Okay. Then I put a tick to labels because I have included labels into my data range. Then constant is 0 is not, so I don't put a tick there. Confidence level is something that we don't know for the moment, so I will not go there. So without that, we can move forward. Right? Then what do we want? So various different options are there, but without selecting those, I will select uh, the output, right, where I want it. I want it here on this page, so I will click here, D1, right? Other things I don't select any, right? Then I click OK. Right. So once I do that, it does the regression analysis and give me this output. Now this output is uh, quite informative and it has a lot of measures that we don't know about, right? But we can find some of the things. However, I have input in the wrong direction, X and Y. Sorry about that. I will have to delete this. My data input was wrong. Okay. Regression, then Y input. Actually, it is Y first, not X. Okay. First is the Y range. My eyesight is poor. Okay. Y. So it is sales. Y range is the dependent variable. So it's range, sales, and X range is the adverts. Okay. Other things I won't change. It is the same. Um, so be careful. Huh? This kind of mistakes can happen. Then I will click OK. Okay. Now I get the output. So you can see here. Intercept. Intercept is in the equation where the line cuts the y-axis. So it cuts here. So it is actually in our equation is the C, right? So you can see it is here, mx plus C, 23.025. You can see it here also. Okay. Then 4.831, 933, right? You can see it here. Okay. You see that? Right. Then we can do estimated sales. Estimated sales value. Okay. Estimated sales value. How do we do that? That is this equation. So I will use these values here to estimate this value based on advertisements. So estimated sales. Okay. Um, so it is equal to, I put the equivalent sign. This value, I will put dollar signs. Right? I put dollar signs to get the to be able to copy it down so that it won't change. Its value will remain the same into X value, right? And that plus the intercept value. For that also I will get the dollar sign with the F4, right? When I press F4, function 4 key, it will add two dollar signs there. Okay, so I get that value, 27.857. Now I copy down. Okay, I have got these values. If I click here, you can see relatively these values are changed because I did not put a dollar sign there, but these two figures have not changed. Okay, they are the same. Okay, so that is the estimated value. I will need few columns here, so I will insert some columns. Make it a little narrow. Right. So that those are the estimated sales. Now these are the estimated values, and these are the sales value. Right. So instead of this one, we try to do this one and see whether we can get it nicely. Hope you can see it. Right. Now, estimated values, you can see they are on a straight line. Can you see? They are on a straight line. Or you can try to add the trend line if you want. Right. So once we add the trend line, you can see they are on the trend line. So that is the estimated line. Okay. So let's get the equation also there for clarity. So it's the same. Got it? So the estimated values are they are on the trend line. That is because the estimated values are based on the actuals here. Actuals here because independent data values, right? So for the actual values of x values of the actual data, right? X values of the actual data, we estimate the y value. Y has to be here, but actually is here, right? So that is what we have. So these are the errors. From there, we have the errors. Okay. Right. So now, if there had been no, let's say, if there had been uh, no other effect, right? If there had been no other effect, assume these variables were not, or the say sales was not affected by anything else, right? Only the advertisement expenditure is affected, which is not really. In reality, it cannot happen because we know, right? Advertisement is not the only thing that affects the sale, but simply assume um, there is no other factor affecting. We have controlled all the other factors perfectly, which is not possible, right? Then, then for these advertisement expenditures, the sales should have been on these orange dots. Hope you understand that. Because nothing else affected, then the theoretical value is the value they should have had. Okay, assuming this line is the correct line. Okay, we have to assume that now because that is the best line we have found. So we assume that that is a theoretical line. Okay, so then say they should have been here, but what really happened was that the real values were away from that, right? The real values were away from that. Okay, so we in a way calculate the mean value of each of these, right? This is the mean value, right? I copy it this way, right? So the mean value of X is, advertisement expenditure is 3.13. Mean value of sales is 38.1. And you can see, interestingly, the mean value of estimated sales also is 38.1, while, of course, these figures are different. Okay, that you can see. So that happens. Okay, because the average of both are at the same, which means they are somewhere here, that is 3.13 and 38.1. Okay, we get that also onto the graph, right? By extending this down. Okay, so we have got it. You can see this here, it have appeared. Okay, so that is also on the line. Mean value is also on the line, estimated line. Okay, So if we consider from this line, right? Now, for different x values, right? So this is the average value. So at average is the say the expected value, right? Expected normal value. So from that expected normal value for different values of x, actually y has changed. Now, even though we put a dot here, but how y have changed is from here to here. Okay, that is the deviation because we are taking both directions only. The dots are coming in this middle area. If you consider only the y values, right, having these y values by disregarding x, right? So the values are actually here. So this one is actually here 30, right? This one is actually here 20 something. So on the y axis. Okay, so if you consider y value, therefore it will be here, and for the other y value here, then next y value somewhere here, the next one, this one, it will be here. Similarly, to the other side also, this value will be here, and the other value will be somewhere here. So that is the y values that is coming from this line for the estimated line, right? So that deviation of y value, right? That deviation of the y value is now explained using this relationship between x and y value, right? Using that equation. Right? How y changes from this average value is explained by this equation, right? So based on that, the y values are changing. Okay, but the actual y values are not really there. They are in other places, right? So these actual y values are also deviated from the average. Now, average of the actual is also on the same point, right? But since both are coinciding, it shows only an orange dot, but actually blue dot is also exactly there, right? For the average value. Okay, so for them, we see these deviations. For this one, this much. For this one, from this average value from here to here. For that one, from here to here. For the other one, from here to there. Other side also the same. Okay, so that one it is here to here. Likewise, you can see that deviation. So you can see those deviations are large. Some are not, some are larger. Okay, so this large deviation is not fully captured by the uh, equation that we have, or the model, we can call it the model, right? So the model that we have, that large deviation is not fully explained, but part of that is only explained by this. The other part is to be explained by other variables. Okay, so based on this concept, we can do something regarding explaining this say fit of the data, whether they are fitting closely or whether they are fitting not that close, they are wide, right? So for that we have a measure, right? How well the data fits to the equation or to the line, right? So to do that, we find the gap between the mean value of y variable and to the estimated values, and also to the actual values of the same, right? So I will do that calculation. This is gap gap sales. This is gap estimate, right? I'll write it like that. So gap estimated is this, sorry, gap sales actual is, okay, I will write it. For actual, I will say A, right? So actual is, say actual value minus, as I explained to you, the mean value. We are talking about the deviation now from the mean value of y, right? Not from the line, nah? Because otherwise, if you take it from the line, of course, for the estimated one, all are, there is no gap, all gaps will be zero. Here we are talking about from the mean value of y, how far it moves. Okay, this is mean value. Then gap from this value to the mean value of that. Okay, so by the way, both are same 38.1. So you can see we get two different deviations because these two values are different. Okay, and the values are negative. Then if I copy this, cannot copy. I should put dollar signs to copy. So I press the F4 here, dollar signs for that. Oh, whatever. F4, enter. For this one also, I click here and press F4 and enter. Now I copy this down. Okay, so you can see there are positive and negative values, and if I get the sum here, this is mean, nah? So I will put it to the next column. So here we have the sum. That is 0. Here also it is 0. So it is not meaning. Why? That is because negative and positive are 14 of each other, and it becomes 0 because average is exactly in the middle of all the data. Okay, then this negative and positive will cut off each other and become 0. So we have to overcome this. So what we do is we square this. Okay, we square this. Yeah, A, we get the square value. Fine. I copy this to financial. I get it fine. Yes, because it is a relative position. I did not put any dollar signs. Okay, so I'm getting. You can see, right? So we have smaller values. Suddenly 141, right? So you can see that is because this is 11.9. Okay. So when it is 3.13, 9.7. When it is say 1.88, it is 3.5. So you can see the larger values, when you square, they become huge. Okay. Now this is the power of gap A. Also, I will see EA power 2. Right. This is gap estimate to power 2. Okay. So if I take the summation here now, I have different values. Okay. So this is the summation of the actual values gap from the center. This is the summation of the estimated values gap. Okay. So if I divide this estimated value gap, right? by the actual values gap, I get 0.64. Okay. Right. If I get the square root of this value, we get the square root, I will 5, will get 0.8. Okay. So if we go here, take this one, our squared value, and see we are getting this value. So instead of going for the square root, we are going with r squared. So r squared, actually a proper way to calculate, we have a, I think there is a different method, but this is the basic concept. Okay. R squared, I can't type here, I will just put R2 here, right? So R squared is equal to 0.64. Okay. Here also you can see that value, R squared. Same value here, 6351. This is rounded. Okay. So the idea of R squared is therefore to figure whether the data is quite close to each other or not, right? I mean, each other means say quite close to the model line, right? Whether the data is scattered closer to the model line or not. Because if the data is scattered closer to the model line, the deviation from the center will be less. Okay, deviation from the center will be less, and that will explain the model line will explain the actual data well with high accuracy, right? So the explained, we can say, right, this value is the explained deviation from the center. Why? Because that is given by our theory. Theory means the line that we found, the model line, right, that we found. Okay. So that is the explanation, explained deviation between of the y value based on the x values. Okay. But this has been the actual deviation of y value for those x values. Okay. So the total deviation is not explained, but only this much is explained. So when we divide the explained deviation by the actual deviation, we get the r square. Okay. So you can imagine if the data had been exactly on this, right? Had been exactly on this line instead of this. Assume we controlled everything. So this will come here, this will come here, this will come here, all will come here, right? Onto the line. So if that happens, you can see these values, right? These values will be equal to these values, actual values, because they are also on the line, right? That means these values will become these values because they come to the line. Okay, so once they come to the line, they will be equal. And as a result, right, this value here, right, will also be this value because that is the same figures. So when you divide that by the same value here, you will get 1 here. Okay, so if the real data lies perfectly on the line, you will get 1 for r square, right? If they are not, well, you will get a number lesser than 1. Anyway, you will not get a negative number, right? But if the data is far away scattered from the line, you will get a number closer to 0. If the data is scattered nearby the line, then you will get a number closer to 1. So if the R square value is closer to 1, we can say our model explains the effect of Y with high accuracy, right? Or we can say, using our model, we can estimate the Y value with the higher precision or accuracy. Because when we estimate a certain Y value, that Y value will be, so say for example, for future Y value. So when we explain now, this is what we have spent so far. So in the next month, if we are going to spend maybe say 4 million, that is this value, right? So here they have got 50, right? But the estimated value is 42.4, right? So if we are going to invest next month 4 million, we are likely to get a sale of 42.4, right? Okay, so just assume we have say uh, items, 40 million worth of item that we want to sell, right? Minimum 40 million. That also we can actually estimate by estimating it backwards using the same equation. Okay, so that one gives us the theoretical value. So if we had the data very close by, that means next time also, when we estimate using this equation, the actual value is likely to become very close by. So if we have a large R square value, that means our prediction will have a higher precision, right? If we have a lower R square value, then using this model, if we do a prediction, our precision level will be less. Okay, hope you got that idea. Any question regarding this? Okay. Okay, it seems that there are no questions, not in the chat either. Okay, so then we can move forward. So that is about the analysis. Now, when we do this analysis, of course, we need data. So when we collect data, we have to concern few things, right? So I will talk about those now. To do that, I will minimize this. Okay, before minimizing this, of course, I want to show you something. That is now, this one we did for a single, or actually two variables scenario. One variable is affecting another variable. Okay, but just let's see if I have that data. Okay, I think I have. Okay, land prices. Now look at this data. Okay, so observation, of course, is not a variable. That is the reference number, observation number. So this data is collected from several plots of land an organization has bought. The property developers do this, so they buy lands and sell, right? So this property developer, I don't know whether they actually develop the land. Very often they just bulldoze the land and sell. So bulldozing, I don't know whether it is development, but it's clean. Of course, the trees are cut down and those are sold separately. Anything else is also sometimes they bring this red laterite and lay over the land and compact a bit so that it looks nice or attractive. Anyway, uh, we'll forget about that. So this is about a property developer who is buying the land, purchasing. Okay. So when they purchase, the data is recorded. Okay. So you can see uh, the per purchase price is there, per unit price is there. Okay. That is one variable. This is unit price, okay, not the price for the whole land. Okay. This is the unit price. Then the distance, right? The distance is the distance from the town center, urban center, right? Distance from the urban center. Because we know that when a plot of land is closer to the urban center, the prices are high. Right? When they are away from that, the prices drop. So therefore, this information is important because, say, there is a relationship between with that we already know. Okay, therefore, that is correct. And also, the size of each plot is also collected because it is assumed that there is impact from the plot size to the land price. Okay, so that is also collected. Now, if you want, you can independently find the relationship between the price and the distance, price and the plot size. Okay. Then in addition to that, we also have this whether there is water supply or not, because we also know when there is water supply, the plot values are usually higher. When there is no water supply, it is less. Here, this one, you can see it is just 1 or 0. So we call these kind of ones dummy variables, right? Dummy, right? Um, so they can have only two values. Okay. Um, but these ones are quantitative data. Now, this one actually, you can see they are qualitative, right? Whether you have water supply or not. It is actually qualitative data. So we have used zeros and ones for that to represent two states of that qualitative data. Okay. So now we need to see what kind of a relationship is there from all these three together to the price, right? When all these three are acting together to the price. Because if you can have a model for that relationship, then we can use that model to estimate price for future purchases. Okay. We don't have to buy the land at the same price, but based on the historical data, we now have uh, an estimate for the future purchase, right? So we actually these people who are doing this business might do the same thing in their mental calculations, but now we are going to do to find that relationship theoretically. Okay, so to do that, we can use our data analysis tool path, right? So we go to data and go to data analysis. Regression. Okay. Now here I have to replace these ranges. Okay. Now one of the thing is that we have to give y range as a single range. So I give this range here. Okay. For x, I can't give variables separately. So I have to give the complete range, right? So therefore I select from here and all three columns, I include them. Okay, all three columns I include them. Now the thing is, say if you had, say assume the price was in somewhere middle, then you can't select all three together because the price is in the somewhere in the middle. So in that case, you have to first copy paste or move that into a side corner, then have the other X variables together, right? That is a requirement. Okay, so where should I get this output? I will just select some place on this. Okay, here onwards, right? Label, I have put a tick because my data contains labels. Things are okay. I click OK. Okay, now I got the regression analysis, right? You can see R square is quite good, 0.85. In the previous case, it was 0.64. Okay. And comparatively, it is a good fit to the data. Then I go to this. Now, this is the model. So what is the model? I just copy these values. Clarity. Special, okay, so it's more like an equation, right? So then to estimate the price, we can say the price is equal to, right? Start with the intercept, just the intercept, that is B naught, remember, beta naught, plus, now we have several X variables. So X variable 1, X2 variables, X3 variables, likewise you can go. Okay. So this is intercept. So just that value plus, okay. Okay. Another row. So these are the coefficients. Where should I put the other values? Okay. I plan to include the values here. Okay. So intercept I don't have. For the moment, I will put 1, 1, and 1 to do the calculation as the new plot of lands X figures. Okay. So so the price is equal to, right, the intercept plus, put a bracket for gravity, distance into distance coefficient into distance actual value, then plus this coefficient into actual value of the plot size, then plus this coefficient into the actual value of water supply, whether water supply is there or not, 1 or 0. Okay. So that is the estimation for a given value, right? So it goes like this. So intercept is the place where all the, so assume this is a 2-dimension, 3-dimension, then 4-dimension model actually, right? So when both distance, plot size, water supply, right? When all are 0, okay, so that is the value. So I will put 0 here for everything, right? So that is the value. So that means, of course, we cannot, there cannot exist a plot at distance 0, plot size 0, and water supply 0 can be possible, but plot size 0 cannot exist, right? Anyway, that is the base value kind of a thing of a plot of land. Okay. Then if we move by say 1 kilometer away from the town center, right? It will reduce the price by negative 2.1 something, by 2.096, that this amount, by because negative means that is because it is negative. So the price will decrease. Okay. So if the distance is 10 kilometers, so the price will drop by 20.96, right? If it is say 30 kilometers, the price will drop 3 times that. Okay. So if the plot size is 1, right? So it will increase the price by this amount, like 0.1, right? If we round it. Okay. So every 1 perch that the plot size is increased, it will increase the price by this. Okay. So if the plot size is 10, so it will increase the plot price by per perch price by 0.9844. That is about 1. Got it? So if there is water supply, the plot value will increase by 14.46494, this value. No water supply, that value will not be. Okay. So this is the base value. I'll copy that as the value, and I will see the gap. This minus this. Okay, now it is 0. So if I put distance as 1, you can see the new price is lessened by this amount. Okay. And it should be the other way, the reduction. This minus this actual price minus the base price. Okay, you can see that happens. So if it is 10, you can see the price drops by 20. So I'll keep it at 0. And plot size, if the plot size is 10, you can see the price increases by 0.98. So if the plot size is 100 perch, you can see the price is increased by 9.84. Okay. So I put 0 to be for the clarity, but 0 cannot be there, right? If there is water supply, you can see the price is increased by 14 point this much. So here you can only have 1, right? So assume there's a plot of land which is with water supply, 100 perch land at 10-kilometer distance from the town center. So the estimated per perch price is this much, 90. Okay, it's 90. So we'll just look at one of the plots. Okay, distance 10, plot size 110. Okay, distance 10.5, plot size is 110. Okay. 10.5, Lot size is 110. Okay, so the estimated value is 90.5. Okay, estimated value is 90.5. We'll see the actual value is 81. Okay, you can see the actual value is not exactly the same, but some closer value. Some of the values may have been better estimated. We can, shall we check this one? A larger value, right? That is 7.7 and 220, and without water. That one is with water, right? So 7.7, 220. 7.7, if you see, without water. You can see it is 92 point something, right? But the sales price is quite high, 102. Okay, so it can deviate in both directions. That is possible. Okay, but using this method, you can um, estimate the future value, or you can use it as a forecasting model. Of course, there will be an error, but this is the best forecast you can make. Okay, so if you learn it further, of course, you can also talk about this is the forecast average, but say I'm confident that this will only change within this range. So when you talk about this confidence, you can say I'm 95% confident it will be within this range. So to that extent, actually you can talk about, but for the moment you are unable. But if you consider this kind of a thing to do with what I will discuss next, I will try to explain this also if I have time. Um, you will be able to say more than this with your estimates, right? Because that is quite important when you are dealing in the building sector, uh, project management. So estimation is one of the tasks that you do. I mean, not only the cost, but various things you would be estimating. So when you have data, you can make a more informed decision by using these techniques. Okay. So, of course, you can't use the graphical technique when you have more than two variables. I mean, more than one independent variable. So, several variables are together affecting, and and you select all these variables and try to figure out how they are affecting. This is the method to use. Okay. Still no questions?
Why is a distance minus?
Distance minus figure came from the data. So the minus means if you write this equation, right, you will write it as, say, I will type it here. The price is equal to, right, I will round it. 87, 87 is the intercept, 87, then minus, right? 2.1 times, I'm rounding, 2.1 times distance plus, I will round the next number also, 0, 0.1, okay, rounded, times the lot size plus 14.5 supply water. Right. Now, what this means is that right, when the distance is larger, the price drops. There's a negative relationship between distance and the price. Right. Between plot size and the price, it is positive. When the plot size become larger, the price increases. This is the price here is per unit price, that is per perch price. Okay, not the whole plot. So per perch price increases when the plot size is larger. Okay, that is what we found. Then if there is water supply, then this will become 1. Water supply value will become 1. Then the plot value will increase by 14.5. If there is no water supply, then this value will become 0. And therefore, 14.5 will not be added to the price. So the price will be increased by 14.5%. Sorry, not 14.5%, 14.5 value if there is water supply. So negative 2, therefore, we get it from the analysis. Here also you can see that. So we get it from the analysis because the relationship between the distance and the price had been negative. Understood?
Yes, sir.
Okay,
Thank you.
good. Any other question? Very good. Good to ask such things which we are not clear, even from anything which I did earlier. Okay. Right. Okay, so if there are no questions, we can conclude. So using that simple equation also, you can only calculate the equation that the equation I presented in my PowerPoint slide. So you can only calculate the equation for a single independent variable, right? If you have, okay, if you have more than one independent variables, then you can't use this. Okay, so if you have only one x variable, you can use this equation. Otherwise, you can't. Okay, so you have that data. Of course, you can try manual calculation for the advertisement and sales example and see whether you get the same answer as in the Excel calculation. It is important that you do this because, actually you have to do it for few other samples also. It is because it is better to practice that manual calculation because there may be, right? Very often I give such calculation for unit SAMs. Okay, simple one, but so you have to indicate or showcase that you actually understand this and can do a simple one and talk about it. Of course, we will have to discuss or interpret the answer that you get. So I in a way interpreted what we got here. So that is same kind of thing that you would also have to do, right? By looking at the coefficients here, right? You have to talk about what they mean, like there's a negative relationship with the distance, and every kilometer that you that the plot is away from the town center, the price will drop by -2. Likewise, you can explain the effect of each variable. And of course, in your example, if you do the calculation, you will have only one such variable. Or if I give the equation and ask you to explain that, then you will have to explain each variable. And of course, you should also be able to talk about the R square value. Okay. Based on that, whether the data fits well to the equation or not. Not the we don't call it the equation, we actually call it the model, right? So this equation is the model, right? So model of the pricing model. Okay. So it explains how the price is built up, uh, right? It is not built up through any chemical reactions or something, right? So it is not that science. So this is basically something in economics, something in social nature. So socially built, right? Those who owns the land also have a certain idea that is socially created about the value of the plot of land. Right? Actually, how we can value a land if objectively like that, right? It's very challenging, right? So based on various things, we have a certain judgment. This land would value about this much. So even the owner would have that judgment and they would sell it around that price. Okay, so that is what is captured. Still, there is error level. Can you see there? So even for two examples that we calculated, there was about 10 units error, right? In the estimate for the actual data that we have here. So that level of error is there, but at least now we have this estimated value. Okay, so that is good. Right, so with that, I will conclude it for today. If you have any further questions, actually, we can discuss. Do you have any? Okay, I will stop my sharing. Right, so,
Good night, sir.
okay, good night, everybody.
Thank you, sir.
You're welcome. Right, so see you next week. I'll end the meeting.